Okay. Okay. Well, thank you very much for the invitation. It's a great honor to speak at the ICM. So this talk is about work I've been doing in the last 5 to 6 years with several collaborators that I will mention as I go along. And it is sort of sitting between statistical inference problems, mathematical statistics, and sort of traditional problems that are studied with partial differential equations, and also more generally the area of nonlinear inverse problems. So if you're interested in this material, this spring I had a visiting sort of sabbatical at ETH Zurich, where I wrote up some lecture notes as part of a graduate course, which you can find on my website. So that should give you some background material and also many references. So I just mentioned that here right at the beginning to advertise it. What is this talk all about? So it is basically, from a statistician's point of view, it is a regression problem. It is a class of regression problems with a particular structure. So we do have sort of the usual setting of response variables yi that we measure and covariates xi that we measure. And we sort of measure a particular function g theta at a bunch of points xi that sort of discretize some manifold or domain that supports these functions. And every time we make such a measurement, there's some additive Gaussian noise. We see the response arising from such a measurement. Yeah? So typically in these sort of application structures that we encounter, the data will take real values or possibly vector space valued sort of responses yi. So there will be some vector space that will generally take a finite dimensions today, or even for the notation often just one-dimensional to streamline the exposition. And just some notations, so we'll call this data vector the actual observations that we make yi, xi. And capital N is the number of such measurements, so the sample size. Yeah? And so the more measurements we make, the more informative we believe our data to be. And these regression fields themselves, so this is a collection of regression maps g theta that are indexed by some parameter space theta and theta. And somehow we can think of the original parameter capital theta that we want to sort of find given the data as indexed by some natural regular function that maybe lies in some Sobolev space H alpha, where alpha sort of measures the number of derivatives, somehow the regularity of the function that we want to sort of infer. But we do not measure this theta function, we measure this g of theta function. Yeah? And sort of this connection between theta and g of theta is sort of described by the solution map of a partial differential equation that arises with some unknown differential operator, where again the theta parameter from before is sort of the thing that indexes the unknown coefficient of the differential operator. And so in inverse problems, in the inverse problems literature, this G map that associates the unknown coefficient theta to the actual solution of the PDE is often called the forward map and can be formalized as just a map G on this theta space, taking values in some L2 space of the manifold where we discretize. And somehow in the applications we have in mind, and that's sort of one of the key gists of this talk, is that these are non-linear maps. Yeah? So we get that this will induce some complications, but they're naturally non-linear because of the PDE structure. Applications of such regression problems permeate all sorts of inference problems with PDEs. You can think of classical X-ray tomography issues where you sort of shoot rays through a certain body and you want to make non-invasive measurements of what is inside. Sort of the class of PDEs that connects to these X-ray problems are sort of transport PDEs. First order equations. Another class of important PDE examples where such measurements occur comes with time evolution equations. You can think of data assimilation, ocean dynamics, weather forecasting, Navier-Stokes equations, sort of any kind of time evolution PDE that you then make measurements of at discrete times and the discretization in space. And obviously you want to sort of infer the underlying dynamics of the differential operator from the regression data you observe. And for the theory, often one sticks to sort of maybe simplifications of these measurement settings where maybe the time evolution structure is sort of encapsulated in some steady state PDE that might be elliptic, for instance, where you can sort of make this theory work maybe at least initially more easily. Yeah. So and elliptic PDEs also have many such applications. Sort of how such problems arise within modern data science has been subject of substantial scientific activity in the last decade or two. There has been a very influential survey paper by Andrew Stuart that I will speak about later in a moment in 2010 in Acta Numerica. And there's also a more recent paper by Simon Erich and co-authors. And there's also a whole SciEM journal on uncertainty quantification that sort of is dedicated to many of these issues when we sort of combine classical inference and parameter identification problems for partial differential equations with sort of writing down a proper statistical noise model, and in particular with high or infinite dimensional parameter spaces, and see whether the algorithms we use can sort of scale up with these things, and in particular whether we can maybe prove that these algorithms work. These nonlinear inverse problems also attract substantial attention in pure mathematics, sort of if you want to make this distinction, where people just try to prove that these G maps, these forward maps, are at all injective, meaning that somehow the problem to identify theta from G of theta is sort of at least well posed in the sense that it is a injective map. And there's a big sort of field of mathematical activity again, and there's a book by Gabriel Paternain, who is one of my colleagues here in Cambridge, whom I learned a lot from in the last few years, and his co-authors Mikko Sarlo and Gunther Ullmann, that is appearing in CUP. So there's sort of a wide background between sort of more applied numerical analysis problems and maybe really the pure mathematics of checking when such PDE structures actually lead to identifiable problems, and sort of the thing where, or the story where that we're trying to bring to this area now is to confront it with sort of high dimensional data science problems. And sort of, if you want to do some prototypical, maybe not toy models, but basic models, fruit fly examples, maybe where we can test our methods first. Here are sort of two sort of classical PDEs that pop up in the literature frequently, where you try to find sort of the conductivity or diffusivity of a diffusion equation from the steady state solution of the elliptic PDE that solves sort of this divergence form equation. And what you should think of is that the regression function you're measuring, the G of theta, is the U that solves this equation for a particular diffusivity or conductivity f theta, that in order to get ellipticity, obviously we want this to be strictly positive. And so somehow the set of regression functions we have are not just like arbitrary regression maps about which we don't know anything, but they are regression maps that are solutions of partial differential equations. So there's particular non-linear, but still particular structural information available. And the question is, how can we take advantage of such information in sort of statistical inference problems? You can sort of, go away from this base PDE and just look at other problems where you have a given differential operator, let's call it D, that doesn't have to be elliptic, could be anything, and you perturb it by a sort of order 0 term and see how the solution of this equation sort of varies as you vary the input perturbation term f theta here. Yeah? So for instance, if you take for D just the Laplacian, you will get a Schrödinger type equation. But if you take for D, say something like the geodesic vector field, you can study a class of X-ray problems in this kind. Yeah? And again, you will make measurements of the solution of this perturbed PDE independence of sort of theta, and then try to infer the perturbation from just having observed the solution of the PDE. And the whole thing, of course, happens under discretization and statistical noise. Yeah, and in these model examples, and also in many of the other examples, the sort of the distinctive feature is that the map that associates theta sort of to its solution U theta is a nonlinear map. For instance, in these two examples, this is easy to see. Okay, so what do people do? I mean, maybe before I sort of, just give you some visual input on what that might mean. No, sort of here's sort of a matrix valued search problem that arises with non-abelian X-ray transforms. So you have sort of a maybe skew symmetric matrix field that is described by these sort of 3 entries. So it's a vector field that you're basically trying to determine these 3 functions that are modeled like as infinite dimensional parameters in some Sobolev space. This would be the theta parameter, but what you measure is sort of the scattering data of some matrix ODE, which sort of collects sort of the line sort of X-ray solutions of this matrix differential equation at the boundary, at the influx boundary. Yeah? And so the picture you would get is then here SU2 valued scattering plots, real and imaginary parts on the left and the right. And so then you observe this with noise, and you want to go back to this theta. And these problems are often quite difficult in nonlinear settings. And let me just give you a few representative properties of this G map that sort of maybe allow us to summarize some of the typical challenges, even, you know, with an eye, maybe if you think of people who don't know so much about PDEs, we might try, so what are the distinctive statistical challenges here that are sort of described by these GMAPs? So the thing is, yes, the solution to these PDEs exists. Yeah, so it's not in one dimension. Of course, we can just write down the solution, but in multi-dimensions, we all know existence of solutions of PDEs usually follows from some result in functional analysis. So it's not that we can write down a formula for how G depends on theta, but it does exist, this map. We can often evaluate it numerically by numerical PDE technique. So if someone tells me what theta is, I can produce a pretty good sort of, you know, numerical approximation of this solution of the PDE. So that's something we can do. Typically, also, these maps are smoothing. Yeah? So this is why these are inverse problems, because somehow if theta is of a certain regularity, then the G of theta will be even a bit smoother. And of course, if the measurement process sort of smooths out singularities, this somehow might mask information in our data. So smoothing things out is not always helpful in statistics. So typically you will map like an L2 function onto some kappa regular, kappa smooth function. In elliptic PDEs, kappa would often be 1 or 2 or something like that. Whether these forward maps are injective or not can be a hard problem that sort of, you know, maybe mathematicians can concern themselves in their own right without even thinking about applications. But often there is some injectivity theorem that tells you in principle the inverse exists, but this inverse is typically not continuous in the kind of topology in which statisticians know how to solve infinite dimensional problems. Yeah, so in statisticians, particularly in Bayesian inverse problems, we'll be able to say that, yes, so in a Hellinger distance or Kullback-Leibler divergence, I can typically make, or prediction risks if you want, I can make inference on my regression function, but the inverse map somehow that would go from my inference on the regression function back to the parameter is not continuous in the topologies that we would like. So I cannot just like feed in some naive plug-in estimator and solve for theta. And at any rate, also there is no formula for G inverse. Yeah? So even if it were continuous, I couldn't write down a even numerical approximation for it easily. Yeah. So we don't have like inversion formulas as we do with Radon or Fourier transforms and so on. Okay. So these are all complicated things in a way, and somehow this set of regression functions is a constrained, a non-linearly constrained subset of the usual sort of space of regression functions that you use when we do non-parametric smoothing techniques in statistics. Yeah? So we cannot really use any of the standard tools from infinite dimensional statistics in a naive way, at least. Okay, well, so there has been a very influential paper in this area by Andrew Stuart from about 10 years, a bit more than 10 years ago, where he advocated that one should just use the Bayesian inference approach to these models where we sort of measure the solution of a PDE discretized plus noise, which is to, well, I mean, you know, what would statisticians usually do? The first thing would be to write down somehow the least squares fit, where I sort of look at how on average in the measurements I have made, the solutions theta, when I compute the G of theta evaluated at my covariates, sort of explains the responses. And I could try to somehow minimize this. Typically, we want to minimize this maybe over some approximation space. We'll get to this in a moment. But we note immediately, because of the non-linearity of the map that sends theta to G of theta, this is a non-convex function. So if I use an off-the-shelf optimization algorithm, gradient descent or whatever, I'm not guaranteed at all that it will find anything better than a local optimum. And of course, these posterior surfaces can be very complex because these PDEs are not, you know, we don't have closed form solutions for them. At the same time, of course, we can use PDE theory to try to maybe understand what the statistical properties of this sort of surface are in high dimensions. Now, what did sort of Andrew Stuart say? Well, okay, so we can just put a prior distribution on theta, a probability measure on this sort of, in this case, function space, because we're trying to model random fields. So ideally, I would maybe take a Gaussian random field on my domain X, that we can formalize this mathematically by a Gaussian process prior, which are very popular sort of statistical inference tools also in machine learning, and they pop up here as well. And the posterior distribution then is just a reweighted version of the likelihood function, which is precisely the exponential of this least squares fit here in the Gaussian regression model that I've written down. So it would be like an expression roughly of this kind, where the reweighting, sort of this Hilbert space penalty norm squared, comes from the Gaussian process prior and is somehow determining the covariance structure of the prior we use. So in some sense, in many of the applications, a representative choice of the reproducing kernel Hilbert space of this prior would be to take for calligraphic H here just an alpha regular Sobolev space. Okay. Now you can ask yourself, once I have this posterior distribution, how do I extract the statistical algorithm from it? Well, I mean, one thing, okay, maybe the first thing would say, I want to take the most likely point under the posterior, which sometimes called the maximum a posteriori estimate, which would basically require you to optimize this functional here, which of course, yes, there's some help from the penalty term here, because sort of at least when the RKHS norm, the Sobolev norm gets very large, this will sort of penalize this, penalize two rough solutions, but it's still a non-convex problem, so it's not clear that you can find these maximizers, and it seems that we don't gain a lot. But of course, once I have written down the Bayesian formalism, I can also do other things and use other algorithms which are not based on optimization, but for instance, Markov chain Monte Carlo methods, which will, when I average over sort of ergodic draws of a Markov chain that is sort of targeting the correct posterior distribution, give me an approximation of this posterior mean vector in high or infinite dimensions. And so the question that arises is, what can we say about such algorithms? But before we sort of, try to discuss this theory, let me just explain to you how such MCMC methods might typically work when they try to compute this posterior mean vector. There are, of course, many Markov chain Monte Carlo methods, one for which we also have some theory that I will show later, arises from gradient-based methods. They're sometimes called Langevin MCMC methods. And so what you would do is, I mean, whenever you implement anything, of course, even if it's in infinite dimensions, you will implement it in a high dimensional space, maybe typically say some discretization of my parameter space, where you could use, at least for the theory I'm presenting here, pretty much anything you like, as long as you can check some conditions. Maybe a popular choice for the theory is just to basically take the eigenfunctions of the Laplacian on your domain, but you could also use wavelets or splines or more sophisticated compositional structures if you wanted to, as long as you can check some of the conditions that we will write down. And then what you do is you just do sort of a gradient step. You set up a gradient step Monte Carlo method where you initialize somewhere. That will, of course, be an interesting question where to initialize. Then you compute the gradient of your log posterior. No? So the log posterior was just basically the likelihood function, the least squares fit plus the prior term, multiplied by a step size delta, and you add a sort of small Gaussian innovation. And so you explore somehow the posterior distribution by going into these gradient directions. So of course, this will kind of accelerate when you go to areas of a strictly positive gradient, but it also has this sort of stochastic term that keeps your Markov chain alive forever, so that it doesn't collapse to a local optimum. Yeah? So this is, of course, important. We want this Markov chain to stay alive, because it should mix towards a non-degenerate posterior distribution instead of just getting stuck at the local mode. And so what you do is you run this algorithm, and you maybe after some burn-in time, you will collect the ergodic averages from your gradient dynamics, and this should give you, at least heuristically for the time being, by the ergodic theorem, a decent approximation of this posterior mean, simply because this discrete dynamics is the discretization of a continuous diffusion process, the Langevin diffusion, which has precisely the proper posterior distribution as its invariant measure. So by the ergodic theorem, you should be mixing towards the right target, and the discretization step, at least when we think of delta small, should not hurt us too much. Yeah? So and you can also try to adjust for the discretization step, but for the talk here, I will not talk about these things. Okay, and so now, what is the clever thing of these algorithms, with regards to nonlinear inverse problems? Well, here we go. If I want to run this algorithm, what do I have to do in each step? I need to calculate the gradient of the log posterior, and that needs evaluation of the log likelihood function, well, the gradient of it, which, if you think about it, needs the evaluation of the forward map G at a point and of its gradient. And so these, both G and the gradient of G, are solution maps of a PDE that we sort of know, and they can be computed effectively by whichever numerical technique you wish to use to solve your PDE. Yeah, and so I can run this algorithm without ever even thinking about, and certainly without computing, the inverse map that I'm actually trying to sort of solve for. Yeah, so that is why these algorithms are very attractive in complicated nonlinear inverse problems, because they do not require a formula or even a theorem about injectivity of G. Now, that is, of course, also at the same time where for a mathematician, it starts to be interesting whether you can actually prove guarantees for such algorithms, because I can actually use this algorithm without even establishing injectivity of G, which means that I have not established that this is an identifiable problem. So I could also use this algorithm without even checking that there is a problem to solve. It could be highly, unidentified, and I could still use this algorithm. So the question is really, what are the sanity checks we can give for such algorithms in these settings? Okay, but it is something that is very popular in applications in this area. Okay, and here I've implemented this with François Monat, who is also a long-standing collaborator on these projects for these non-abelian X-ray transforms, and you see. So here the MCMC is run for 100,000 steps. So, and you report sort of the averages after some burn-in. And then in the first row, second row, third row, you'll see the result of the posterior mean computed for sample sizes, statistical samples of just very moderate sizes, 200, 400, and 800. And the last row really looks very much like the ground truth from which these simulations were performed. So you see that potentially, even in very non-linear, non-convex problems, this methodology can be very successful. Yeah, and many others have implemented this. And somehow, what we've been trying to do in the last 5 or 6 years is to produce some theory for the success and also the limitations of these algorithms, and when we can actually trust them as scientists and as statisticians and ultimately as mathematicians. Okay, one buzzword that pops up in this context very often is uncertainty quantification. Even the SIAM journal is called SIAM Journal on Uncertainty Quantification, where many of these algorithms are proposed or studied. And so what does that mean? Well, it can mean many things. For a statistician, the most tangible notion of uncertainty quantification is related to what we call confidence sets, or maybe credible sets. Is what you would do. Well, okay, if you think of the algorithm that you've used, well, you've run your MCMC for a long time and you've computed the average, which maybe you could think of the blue line here in the left plot. And then, well, the true curve you can usually not plot in the real world, but we've plotted here for the synthetic data. But what you can also do is you can plot all sort of this function cloud that arises from these MCMC draws, and see how they sort of scatter around the posterior mean that you've reported. And this should give you sort of some corridors that look like this, and they might suggest something like an error bar or an error curve in which you believe that your true function might lie. Now, of course, the way the quantiles of these error bars in these red pictures have been chosen depends on the posterior distribution, and these are not a priori proper statistical confidence sets. So if I use them in scientific applications, I might actually just be reproducing the randomness of the prior and I might not be saying anything of any statistical significance. And it's easy to come up with simple misspecified statistical models where you just change the prior to be wrong at the boundary here, and so the construction collapses obviously then at the boundary because you're not modeling your function correctly. But actually the misspecification, because of the non-locality of somehow the way these measurements occur through PD forward maps, propagates into the interior. Yeah, so whether these are actually proper confidence sets or not, in a statistical sense, that I can give you some sort of conservative guarantee that the true function will lie in this cloud curve with high probability, this is really not at all obvious. Yeah? And so what I want to talk about sort of in the second half of this talk now is basically to give you some of the theorems that we've proved in the last few years, and maybe discuss a little bit where this area is going now. Yeah. So there's several, but at least 3 important questions that you can ask in this setting. The first is sort of the sanity check, is something that we call statistical consistency. Does the posterior distribution that we get on the theta parameter, so not on the G of thetas, not the regression maps, but we don't really care about them here. We want to actually find the sort of the coefficient of the differential operator rather than the solution. Does this posterior distribution actually start to concentrate and put almost all its mass near sort of the ground truth that in our mathematical analysis we postulate to have generated the data? And you can ask whether the posterior distribution or its mean is in the right place. Does it actually consistently solve the problem, or is it just like somewhere completely in the wrong area? Once you've proved something like that the posterior distribution sits in the right place, which is a statistical result about the sort of statistical properties of posterior measures in higher infinite dimensions. Once you've done that, you can ask yourself, okay, well, that's all very nice if the posterior sits in the right place, but when I use my algorithm, I'm actually not using the posterior, but I'm using some MCMC approximation to compute the posterior. And so there is a computation error that in particular in high dimensions may, of course, largely dominate the statistical error. So I need to think about that as well, whether these posterior distributions are actually computable, particularly in these sort of non-convex or, if you want, non-log concave examples of posterior distributions that come out of these PDE examples. Yeah? So the question is, can we reliably compute the posterior, or is it basically NP hard? No, I mean, it could be that this is basically not computable because we're trying to sample from a high dimensional non-convex, non-log concave distribution. It could have many little modes, and okay, yes, the MCMC method will not terminate in a local optimum, but the time it needs for this Markov chain to mix and wander around the whole surface of the posterior distribution might still be so long that I will never see in finite time any kind of convergence that I can trust. Okay, so this is certainly just as an important question as statistical consistency. And then the third one is related to the last picture I showed, which is whether these error bars or error regions that one reports can actually be trusted as scientifically reliable predictions of where the ground truth will lie within my MCMC curve clouds. Yeah? So can these error bars be proved to be valid uncertainty quantification? All very hard questions. We have theorems that answer all these questions, partly in the affirmative and sometimes also in the negative, for several examples by now. I will give you references at the end. But in a nutshell, next to sort of statistical properties of high dimensional models that we have studied sort of in detail in the last decade or so, the PDE structure comes into the story in several places, and of course the analytical properties of this G map and also of its linearization play a crucial role. And I want to give you a few sort of insights on how G and this linearization in function space sort of determine statistical and computability aspects of these problems. Okay, so the first question was posterior consistency. And we typically want to prove theorems for algorithms that people actually use, and very popular algorithms are based on Gaussian process priors. So the first challenge was to prove that posterior distributions can concentrate sort of near this ground truth parameter theta naught, maybe at some contraction rate at which the posterior sort of collapses towards this Dirac measure at the ground truth. Sort of, you know, when the prior comes from a Gaussian process prior. And once you have a theorem like that, if you have a bit of uniform integrability in your posterior, some kind of, you know, higher moments, then you typically can also deduce that the posterior mean vector, which is the thing you typically compute by MCMC, does inherit the same convergence rate towards the ground truth when you sample from the ground truth. Okay, so this is sort of the kind of theorem that you would like to kickstart the story of algorithmic guarantees. And sort of the first rigorous result of that kind for Gaussian process priors was proved with François Monin and Gabriel Paternine in a paper last year, where we showed for a particular inverse problem, but where it was clear that the template of the proof covers other settings as well. And there are many follow-up papers that you can find quoted in my lecture notes, that you can determine a contraction rate that is actually algebraic in inverse sample size for this posterior and also the posterior mean. And what this precise power up here depends on, well, it depends on lots of things, on the dimension little d of the domain on which your problem is posed, on eta, which comes from a stability estimate about which I will talk in a moment. Kappa is like the ill-postedness of the problem, and alpha is the regularity of the ground truth. So you can typically drive this rate to the optimal, like 1 over square root n rate when everything is very smooth. But what the optimal exponent is for low regularities is not something we've made so much progress yet on. We're just trying to get these algebraic rates at some decent rate. And what is the key input to prove theorems like that? Well, there are two things. One is, for the statistician, there is a relevant information distance on the space of experiments that create your data, which is called the Hellinger distance, which I will not define here now, but if you don't know it, it's easy to find in my lecture notes. And we prove sort of for these natural PD models that this is, in this random design regression model we have, that is sort of equivalent to the L2 distance on the G of theta. So now this is just a mathematization of what I said earlier, that statistical methods based on likelihood and least squares fits, they will be good in principle, when you can, if you want to recover the regression function g of theta. But of course, we do not want just that. We actually want to go back to theta. And the way to connect these Hellinger distance results that are well known sort of in the literature by now to our inverse problem is to get a stability estimate of this kind, where you sort of say that the distance between the parameters that we're actually interested in, sort of the implied distance by the solutions of these PDEs that correspond to them, can be controlled by somehow a quantitative injectivity estimate, if you want, that sort of tells you, without giving you an inversion formula for G, it tells you at least sort of how stable this map is. And so if I know that I can drive this error to be small, well, at least up to taking the power eta, this will also give me a convergence rate for theta. And we could prove stability estimates like this for a variety of such PDE inverse problems. And you can, again, look at the lecture notes for references and details. But this is something that should be fairly robust for many of these nonlinear inverse problems, that even though we cannot prove an inversion formula, the injectivity theorem often gives you some quantitative methods, maybe by using sort of holomorphic integrating factors or things like this to get an inequality like this. Yeah? So this would be a way to prove consistency. And you can look at the papers for details. Now, the next question, of course, is computability, which is already, I mean, I wouldn't say it's more subtle because consistency is just as hard, but it sort of leads to yet more subtle or sort of more detailed properties of the G map that we need to study. Particularly the way we have analyzed this problem so far is by studying the linearization of the G map. So there's a nonlinear map as such. So you can look at how, when I change the argument from theta to theta plus h, how I can describe sort of the variation in the values the function takes, and I will sort of typically get some linear map acting on the perturbation h, and I want to control this in the usual way of derivatives. And if I have such a thing, which again for PDE problems can typically be done by studying inhomogeneous PDE problems, you can formulate a condition on this derivative that comes up out of this linearization that will allow you to give some computability bounds. And now here again, as I've said, when you run MCMC, you typically think of a high dimensional approximation space that has to be chosen such that this linearization also has some quantitative injectivity, in the sense that this linearization map evaluated the direction h can only vanish when really h is itself 0, and otherwise it cannot be too small, depending in a way that depends on the size of the h you feed in, and perhaps some sort of at worst polynomially decaying constant in dimension that has to do with sort of the ill-conditioned nature of the inverse problem you have. Yeah? So again, this gradient stability condition, which has to hold only at the true value, and maybe then by continuity also in the neighborhood of the true value, is something that we checked. This often requires some real work, but sort of for Schrödinger equations and for some elliptic equations and non-abelian X-rays, we can determine values of kappa that are reasonable, say between 0.5 and maybe 6, that allow you to check this condition. Yeah? So not only is the G map sort of quantitatively injective, but also the linearization. And how this relates to statistical properties is that somehow it tells you quantitative properties about the so-called Fisher information in high dimensions that sort of tells you that what describes the local curvature of the log likelihood function, says least squares map, can be sort of encoded in this G prime. And under this condition, plus a few more technical conditions that I will not write down here, you again look at the lecture notes for detail or the papers, you can show that indeed you can use this gradient-based MCMC method with a slight tweak if it is properly initialized, to actually get a mixing time bound for this Markov chain. And then also you can show that the posterior mean is computable in polynomial time, where the number of iterations of your Markov chain scales polynomially. And what are the quantities we want to be polynomial in? Well, initially, the most important thing is the dimension. So it does not depend exponentially in dimension, which is sort of a danger here. Then, of course, also the noise, the precision level epsilon that you prescribe yourself within which you want to recover the posterior distribution should also not grow exponentially. And also the informativeness. Of course, if I have a potentially multimodal distribution, then the size of the spike that I have to travel down to get on to the other side will, of course, depend on capital N, because my potential, my Gibbs measure I'm sampling from is sort of E to N times something. And so I need to overcome these hardness barriers, both polynomial time in N and in dimension. Yeah, and this algorithm under this condition can be shown to do that. How do we prove that? Well, the starting point are recent theorems that tell you that when your target is strongly globally log concave, which our posterior distributions are of course not, but when that is the case, gradient methods, gradient MCMC can be very fast, just as fast if you want as convex optimization techniques. And so there's sort of almost a little duality between these results. And you get some nice Wasserstein mixing time bounds for these discretized large event diffusions for strongly log concave targets. Now, of course, our targets are not log concave, but under gradient stability, the average log likelihood criterion that sort of pops up in the posterior distribution centrally is locally convex, or if you want, the negative is concave, near the true value. And this can be used to prove just by the usual principle that the Fisher information matrix can be characterized by second derivatives or first derivatives, if you're well specified. This can be, and concentration of measure, this can be used to prove that actually under this condition, at least locally near the ground truth, near the parameter where the posterior is also putting most of its mass, you do have local curvature. Yeah? So the Hessian of the log likelihood function actually is sort of nicely curved, strictly positive definite, even with n times whatever your ill-postness is. Yeah? And this can be proved by concentration of measure tools. So this is hard work, but follows more or less sort of established techniques from our field. And then once you have that, once you know that you're locally log concave, you can just brute force concavify your posterior distribution so that it looks like really nicely bell-shaped. And why do you not incur too much error when you do that? Well, because of the statistical consistency result that I've just showed you before. So what we said, we have some curvature precisely in the area where the ground truth lies, and the posterior puts almost all of its mass precisely where the ground truth lies. And if I can somehow quantify the size of these regions, and sort of quantify this effect about which I just spoke, then if I can initialize into that region, I can actually show computability. Okay, so even though things are not log concave, they're well approximated in Wasserstein distance by a log concave measure. And if I can find this log concave measure, which basically means to find its centering approximately, and that's the problem of initialization, then you can get into the right place. Okay, and you can then get these polynomial time mixing bounds. Okay, so what it tells you, again, to just reiterate, is that because of PDE structure, we do have at least local curvature in these problems. Yeah? So somehow the injectivity nature of many of these G maps comes with a stability estimate, both for the G map and its linearization. So I do get some curvature locally with high probability. And this drives the computability at least near the ground truth parameter, theta 0. And the posterior puts all of its mass precisely there where it has curvature. Okay, and so sort of that is good news if you believe that you can initialize. Now, so of course you can say, well, okay, initialization, I mean, even if you initialize into the right region, your MCMC might still be stuck by multimodality issues, but what we say here, with high probability, this will not be the case. Now you can ask yourself, what happens if I cannot initialize? And so in the spring, when I was visiting ETH Zurich, I was visiting Afonso Bandera and his group, and we sort of discussed this issue at length. And it's a subtle issue. There's some very nice papers by Jarab Benarous and co-authors that give sort of explicit exponential hardness results for MCMC methods in models coming from statistical physics, like sparse PCA, spiked tensor models, and so on, where they show quantitative hardness results for MCMC. And sort of the discussions we've had ultimately seem to be leading to a result that we're writing up at the moment, where you can show that if you actually stay in a class that is locally log concave, but then maybe away from the region where you're locally log concave, you start to still in a unimodal way flatten out maybe, but not because of having multimodality. It's still a unimodal distribution that sort of decreases maybe at least linearly locally. Then if you happen to initialize your MCMC in the wrong place, like too far away from the region of log concavity, you run into a hardness result in the sense that the time it will take your MCMC to travel to the center of the distribution where all the mass lies scales exponentially in dimension. If we assume here that dimension over n goes to a constant that is strictly positive. Yeah? And this, shows that some of the existing results by Hager, Stuart, and Forma on mixing times of dimension-free mixing time bounds for some of these Markov chain methods need to be read with a certain caution. I mean, they're certainly mathematically correct, but they are dimension-free, but they depend on some other constants that actually will turn to scale exponentially in the n, which sort of measures the spikedness. So if you have a very spiked high dimensional distribution, many of these dimension-free mixing time bounds that come from some, maybe ergodic theorem in infinite dimensions or Harris theorem in infinite dimensions, they will actually not give you computability of the posterior distributions. And the only way I see at the moment is to kind of get some local convexity expressed by expressed by virtue of PD bounds to show that when you initialize into that region, you can compute. And if you're outside, of course, for these PD models, it is very hard to say anything about how the curvature behaves when you go beyond the local concavity. I mean, locally, everything is driven by the gradient of this forward map. As you go away, other things start to come into the equation, and understanding these trade-offs for PDs is very hard. And so in general, we cannot rule out that the PD models are also in this kind of class of counterexamples that underlie these theorems. And so I should also say, when you think about these problems, the challenge really is to give polynomial time guarantees that hold simultaneously in dimension and n. Usually just doing d and not n, or n and not d, is kind of significantly easier. I mean, not trivial, but still easier. But doing it simultaneously is hard. And this is, of course, exactly what the statistician is interested in, because we want to show that posterior distributions remain computable even in settings where we have lots of data and lots of dimensions. And we're not interested in sort of the uninformative case where the posterior is just flat and doesn't tell us anything. And if we can initialize, warm start MCMC can be expected to work. Cold start MCMC is probably a story that we cannot expect to work. Okay, so just in the last 2 minutes, I have not spoken about this uncertainty quantification business. There are some results as well. You can look at this in the notes. Maybe just to wrap up, in the last 10 years, I mean, Bayesian inverse problems have been very popular because there is a need in complicated data science problems to quantify the uncertainty in your algorithmic output. And if you don't want to think too much about what you're doing, you just want to get a quick off-the-shelf method, then Bayes methods give you credible sets and error bars straight away. Using them in non-convex high-dimensional problems, is not something we can trust naively. There's certainly no off-the-shelf theorem that Bayes methods always work. It's easy to give counterexamples, but probably well-chosen methods in PD settings that we understand enough of can be trusted. At least there are some theorems now that support such statements. And there are certainly interesting questions for statisticians, for numerical mathematicians, and for pure mathematicians. And there's obviously much more to be done. If you want to read up on some of these papers, so there is lecture notes, which are on my website for now. They will be proofread for the next year until this appears. And here are some papers for those who want to kind of go into the more specific references. Okay, thank you. I'll end here.
Thank you very much. So thank you very much for this beautiful lecture that includes wonderful connections between statistics and PDEs in via inverse problems. I would also thank the audience for participation. Unfortunately, there is no possibility of questions and comments. So if you have questions, please send emails to Professor Nickl. Anyway, I believe everybody has enjoyed the lecture very much. So we close the session with applause to Professor Nickl. So thank you very much, and bye-bye. Thank you.